Hello, my name is Rudra Krishnamurthy, and today I'm going to take you through an introduction to relativity. So what do most people think about when they hear the term relativity? Well, they might think of someone like Einstein with his long hair and his genius ideas, or they might think of something like time travel. In reality, relativity in all its forms is much more simple, but also much more complicated than all of that. There are three main aspects to relativity, and we'll cover some of them in this video. Number one, there's Galilean relativity. Number two, there's special relativity, which is titled special relativity, as it is an isolated case as of the number three, general relativity. Galilean relativity is relatively simple, and you can probably grasp it in this video. You can get an intro to special relativity in this video, and also the basic maths behind it in most college classes, and can even be done with high school algebra. But general relativity usually requires higher education, like a master's degree, and advanced things like tensor calculus or vector calculus. So today we're going to go over Galilean relativity and a small bit of special relativity. So let's start with Galilean relativity. Before 1632, it was assumed that space and time were constant, and in many ways that notion still holds true in many parts of today. If I am walking down the street, then you can map out the whole street or the city block just from my frame of reference, and all look the same for every observer on the street in my point of view. In addition, time is constant. 1 second for me is 1 second for you, and vice versa. However, this is not true, as we'll see in Galilean relativity and in things like special and general relativity. In Galilean relativity, which is also known as Galilean invariance, which is introduced in 1632, Galileo postulated that Newton's law of motion. So basically, object at rest will stay at rest unless acted upon by an outside force. The force equals is a product of mass and acceleration, and also each action has an equal and opposite force. Galileo postulated that all of these three laws of motion are the same in all inertial frames of reference. So what is an inertial frame of reference? That is a frame that is not accelerating. So basically, examples of this would be like one's living room or a cruising airline. So what exactly does this mean? Galilean relativity shows that there is no universal velocity for each object, and this can be summed up through the equation below, that the velocity in one frame is equal to the velocity in the first frame plus the relative velocity. But what does this mean? Let's start with a simple example. If I say there's a stationary observer over here, from this person's point of view, there's a car over here that is going at 60 meters per second in this direction. Meanwhile, they also see a car going in this direction on the other side of the road so they don't crash at 50 miles per hour. 50 meters per second, sorry. So then, so these are the velocities from this observer's point of view. But when you take it from this car's point of view, we see that the velocity, when you take it from car A's point of view, we see that the velocity of car B is not 50 meters per second in that direction. It's actually 60 plus 50 equal 110 meters per second in this direction. So basically what this means is that there is no universal velocity for each object. The velocity that you perceive is dependent on your frame of reference. For example, just because the stationary observer sees that a car A's velocity as 60 meters per second and car B's velocity as 50 meters per second, doesn't mean that that is the universal velocity. In fact, there is no universal velocity, since from car A's frame of reference, given that it is inertial, then car B is going at 110 meters per second, and from car B, it sees A going at 110 meters per second. So now we have established that space is not constant, but still time seems to be constant. However, now we find out that, now let's skip forward a couple of centuries and go to James Clerk Maxwell, an English physicist. In 1864, J.C. Maxwell concluded that light is an electromagnetic wave, which is basically a wave propagated by electric and magnetic fields that's going in a perpendicular direction to both. So, and then he also, through his calculations, he found that light always travels at one constant speed, no matter in a vacuum, which is approximately 3 times 10 to the power of 8 meters per second. In the future, we will represent this number as c. So now this is actually a very specific prediction, and he only found one number. This number doesn't change based on where you're shining from, or where you're shining the beam of light from, or what velocity you're going at. And since it's a very specific prediction, this upends our laws of physics, as we'll see before, at least the ones that are established by Galileo. So Einstein realized that if you are moving at the same speed as the electromagnetic wave, that is 3 times 10 to the power of 8 meters per second, the electric and magnetic fields illustrated above sustaining the wave would not change from your point of view, and as such there would be no wave. That in turn means that for one observer there would be a wave, and for another there wouldn't be a wave. However, this is not possible, so it stands to be deduced that you cannot travel at the speed of light. And this is one of the most important parts of the theory, as we will see later on. If you study this in the future, it is impossible for any particle to travel at that we know of currently, at least, to travel at a speed faster than c. So then, from this new knowledge, Einstein decided to generalize Galileo's principle of relativity. Galileo postulated that Newton's laws of motion are the same in all inertial frames of reference. Einstein took this farther. All laws of physics are valid in all inertial reference frames. That means the speed of light is also valid in all reference frames, which creates one of the biggest discoveries in the history of physics. We see that if an observer is moving in frame S, if this observer is moving is staying stationary, then they see the beam going at speed c to be traveling this far. Okay, but then if there's another frame of reference, frame S hash, this one, and then they are going at another speed. They still perceive light to be traveling at the same. They still perceive the light between them to be traveling at the same speed. However, the distance between them is much smaller than the distance that the light travels for this observer. So what does this mean? Since the speed of light is constant but the distance is different, this means that since the speed of light is equal to a distance over time, this is just the derivation of the formula d equals rt, distance equals rate times time. We find that since c is constant, t must change. Therefore, time is not constant, which means that time is not constant, which is the main finding of special relativity. Previously, at the beginning of history, or at least at the beginning of modern mathematics, we thought that both space and time were constant and unchanging. With Galileo, we found that space is changing depending on where you are and the velocity at which you're going. So space changes depending on which inertial frame of reference you're in. However, by Einstein's deduction, we find that time is also relative. So once we figure out that both space and time are relative, we see that this creates a whole new region of mathematics to explore, which concerns itself with special relativity, which simplifies to the study of things going at very high speeds, and general relativity, which focuses on gravitational effects. So I hope you enjoyed this video regarding an introduction to relativity, and thank you very much.